What I want to do instead is give you guys some new tools, a new way to look at solving really hard coding issues. And this isn't a silver bullet. This isn't to replace OOP or to replace imperative. It's just, hey, here's some new cool tools I like to use. A little bit about me. I'm Timi. I am the lead JavaScript developer for a firm in Knoxville, and I'm a functional-ish developer. I don't do Haskell. I don't do Elm. I'm not that smart, but I want to be one day. You can find me online at those places. Don't, but you can. And what we do and what we hope to get paid for is really hard, right? We have to think of solving these really complex logical issues in a way that we can explain it to a computer that really only understands push, pop, and compare, right? Everything we do in whatever language we do has to be boiled down to a really simplistic, stupid machine. And what we want, or what I see we want with libraries and frameworks and copying and pasting off of Stack Overflow saying, why doesn't this work, is we want to be able to reuse all of our solutions. We don't want to be stuck solving iteration for every new data type. We don't want to be stuck solving 90% of the same problems over and over again. Because when we don't have to do that, when we can start focusing on that unique 10%, we can do what they're doing at Oak Ridge. This is origami. Basically what it does is it queries 75 million nodes of strings, and it comes up with how these strings are related to each other. And it does this on the ectoflop scale, which I don't even know how many zeros that is. And the only way you can do stuff like this, the only way that we can actually focus and do machine learning is if we don't have to resolve problems over and over and over again. And this idea of reusing our code, this idea of solving a problem once, Joe Armstrong in Coders at Work says, object-oriented lacks reusability. You cannot reuse a solution from object to object, as Joe Armstrong says, because of this implicit state. And it's this implicitness that I think I didn't understand. I didn't understand the ramifications of it. And Joe says, when you wanted a banana, you wanted one tiny part of your code, but when you try to pull that out, you get the banana and a gorilla and the whole jungle. You don't just get that small part. So let's look, right? I'm talking about all these words. What am I talking about? This is a constructor function in JavaScript. It's kind of how we cheated classes back in the day. And your boss says, hey, I want a student type. So you create a function that takes in some variables and returns you an object. And this object has some state. And because we're super good at OOP and we're following all the rules, we have some getters and some setters, and we carry along the methods that manipulate the data with the object. Because like they say, in the Tao of objects, this is safer, this makes sense, this is more convenient to have the methods that manipulate our data tagged along with the data itself. And you're doing great, your boss is happy, you're getting high fives, and your boss says, hey, I want a new data type. I want a data type of lists of these objects. And you do your getters and some setters, and then you run into a problem that you've never solved before. Here it's Ray student level, and we can all kind of rationalize how this is done, but this is just a representation of a problem you've never solved before. And you don't know how to do this. You don't know how to manipulate this data structure that you've made up in your head. So what I do is I go down an abstraction. I've abstracted away an object-oriented, and I'm dealing with this student list, which really isn't a thing. It's all in my head. And the way that I solve it is I go down into imperative. And imperatively, we can make an effective procedure really easily, right? Given a list and given some random number, I can make a for loop and do what I want to do with these objects. And it works. And then we spend time refactoring and abstracting it into our class. And we're happy, and your boss is happy, and she is giving everybody high fives, everybody gets pizza parties, and then she says, hey, you did 90% of this over here. Reuse that and change this tiny bit. You figured out this problem of iterating over a list. Now change one tiny part of it. And the thing is, you can't do that and not repeating yourself. Your solution here is stuck. It's stuck with students, it's stuck with level, it's stuck with set level. And the only way to reuse this is copying and pasting and changing half of the code. So Simon in Coders at Work, he says, when the limestone of imperative is washed away, the granite of functional. It's pompous, it's grandiose, but just like we couldn't solve something object-oriented, and we had to go down into imperative, when you can't solve a solution imperatively, you'll find yourself going down into functional. You'll find yourself trying to solve this problem in a functional way, and here's a really cheap solution, right? When we want to raise the student's level, or we want to get their GPA, all we're really doing is changing what happens during each iteration. We're changing one small function, and everything else stays the same. So what we can do is write a higher order function, a function that takes a function in and does something different. Now, anytime we want to raise GPA, anytime we want to do something for every item in this.students, we have an easy API of doing that. And we don't have to repeat ourselves, we're having dry code, we're following all the best patterns, and we look super cool in front of our friends. But what if we wanted to do faculty? What if we wanted to do the student-teacher conference stuff? What if we just had a list of numbers that we wanted to do something with? We got to go one step lower. So we abstract the problem away instead of abstracting the data away. So here, we take our this.forEach student and make it into for each. And this function takes an array and a function. Now, any array given to it, it will do the same thing that this.forEach student did, but for this array given. So for each, we pass it student, and we pass it an anonymous function. And that's great. High fives all around. We're sharing this code. We have solved the problem, and everybody's super happy. And then your boss comes up and says, okay, what I really want you to do now, instead of doing something, instead of just affecting this implicit environment around you, I want you to create something. I want you to take some information and change it into what I want. And we don't know how to do this, but we do have a for each function. We do have this idea of iterating, so let's use that. Let's see how we could use this idea to create a new array. And imperatively, almost, we could say, okay, I have a list. I want to make a new one, so I'll set this up somewhere. I'll create a function. Okay, cool. And then I'll just do for each again. But what are we actually doing? What is the problem we're trying to express to our worker? What is the actual thing we're trying to tell our worker to do? And more importantly, I feel, is how can we reuse this? This is hard. We don't know how in the world we're going to do this. So how do we limit the amount of times we have to solve this problem? Luckily for us, we have this idea called map. Right? It's just like in math, where you have your domain and it maps to a range. F of x equals y. And this is basically what map does. So map, given a list and given a transformation function, it will return to you a new list. Does this kind of make sense to everybody? If not, it's going to get really confusing. So, okay. So, and this is kind of how we use it. It looks a lot like our for each. Right? We have our student list, we have our transformation function, but here is a very slight difference. Everyone that I teach this to, I have the privilege to teach a lot of junior developers about these ideas. And everybody thinks that for each and map are basically the same thing. But map is a value. Map of students and this graduate student function is actually a value. So we can assign it to something. We can tell our worker, hey, the result of this function is now our new students array, while for each does something. For each affects this implicitness. For each changes the state of your code, while map changes the data of your code. And this idea I like to think about as pulling versus passing. When you do for each and you're doing object-oriented and you're doing implicit environment, you're the crane operator. And if you're the crane operator, you have to know, is Jeff back from lunch? Is somebody touching this box that I'm moving? Is this guy gonna go to the right or the left? You have to know everything around you, and you are in charge of that. And if you mess something up, is it your fault? Is it the box's fault? Is it the guy who was supposed to do something before you got here's fault? There's no way to tell without knowing from a 10,000-foot overview what everybody's doing. And Joseph Weizenbaum, in the book Computer Power and Human Reason, says that this pulling of info isn't where the computer gets its power from. The computer gets its power from manipulating information. The power of our computer is to take a 0 and a 1 and produce a 1. It's to take a 0 and a 0 and produce a 0. It doesn't just transfer some information. It doesn't move information. It transforms it. And this transformation is kind of like this trash chute, right? When we map something, all we're doing is we're taking an item, throwing it down a tube. That's all a one worker has to do, and another worker just grabs whatever falls out of the tube and puts it in a new box. And we as the developer, our only concern is that red tube. We're not concerned if it's Tuesday, we're not concerned if it's raining, we're not concerned if someone's called out sick. All we're concerned about is how we transform the information, how we take a box and we smooth the edges out, how we take a number and we transform that into a new number. And this, to me, is a lot less cognitive overhead. I'm not in charge of everything around me. I don't have to worry about everything around me. I have to worry about, given an input, how do I make that input an output that I can use later? Okay, so what in the world about higher order functions, right? That's what this whole talk's about. That's why you guys are here. And that diagram makes no sense to me, and I know what I'm talking about. So, all a higher order function is either a function that takes a function or a function that produces a function. We're not even going to talk about the function that produces a function. We can go into code later. I'm totally down. But we're going to talk a lot about a function that takes a function. And as we've seen, we've built two of these already. Our for each function took a function, therefore it's a higher order function. Our map function takes a function. And what makes this so powerful, what makes this such an amazing idea, is no longer does our functions have to know what they're going to do when we write them. We can write our functions and our code in a way that says, hey, at some point I'm going to tell you how to handle this. But here's the 90% that's never going to change. This 10 unique, and maybe it's only 25% that's the same. Maybe we can only reuse 25% of our code, but that means we get 25% extra time to solve bugs, 25% extra time to do cool stuff, to do reactive stuff, to do amazing GraphQL things, right? So I like to think of all these things and how I can apply them. So we're going to solve a problem. I was given this at an interview, and I thought it was the coolest problem in the world, so we're going to solve it. It's basically given a board and some rules, draw the board as you move around. The board comes in as a string, and blah, 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 but we can basically break this down into one simple problem at first. Is if I'm given a board and I'm given a center and these rules, how do I draw the board? I have no idea. I stood at my computer and I thought, and I could not figure this out. So, how are we going to do it? Are we going to do this class? Are we going to do this stateful idea? Or are we just going to do an array of arrays and do functional? And we're going to ask ourselves why. And this why, why we choose whatever we choose, should always be driven by when I solve this problem, when I finally find my solution, which one's more reusable? Which solution lends itself to be used over and over and over again? Is it this, where we have a class called board, and at somewhere in this class we have some state, and this make board function is going to interact with that, right? Or are we just going to say, hey, I'm going to give you all the information that you need to solve this problem, and you're going to do it? And these are the questions that I had to ask myself. So if I'm talking to my object and I'm like, hey man, I want you to build a board, when I call that function, when I call that method, is the board always correct? Do I have a contract with my worker saying, hey, if I ever ask you to make this, that board that you're going to look at has to be the right board? But what if I want to practice a move, right? What if I want my computer to learn? What if I want to tell my computer, hey, figure this out, I don't care which way you choose, just get to the right place? If I'm interacting with this implicit state, if I'm touching things outside of the function, I can't know the board's always correct. And maybe when I make this board, I'm actually affecting the board instead of just practicing the board. And if I'm doing those two things, what if another function that I wrote is actually changing the board as I'm practicing, or changing the board as I'm doing something? We're the crane operator here. And when we start moving things around and changing state and changing the environment that our code depends on, we have a lot more troubles. We have a lot more bugs. We fail far more often. Because this is how our computer works. This is the fundamental way that the computer thinks. It says, this is all I know. This is my scope. This is my closure. This is my state. You tell it to do something. And then it goes, cool, I'm going to do these steps. I'm going to do this effective procedure. Now I know this. It doesn't care. It doesn't care what's in each state. It doesn't care what the action is. It does exactly what you tell it, and it produces exactly what you told it to produce. Joseph Weizenbaum says that a computer is an embodiment of a law. It is an embodiment of what you as the developer told it to do. And when you don't understand that law, when you don't understand these steps, you are a slave to a capricious law. You are like a clockmaker who shakes the clock and goes, it works now. I don't know why it works. And I've done that so many times in my code, right? I don't know why something's not working. I'll throw in a number, and it just kind of works at that point. And now from that point on, I am scared. I know it's going to break at some point, and I have no idea why. But like I said, I want my computer to learn. I want to not have to worry about these things. And this is what I want my computer to do. I want to declare two different states. I want to say, here's where you're at. Here's where you're going. Figure it out. I don't care how. Because to me, I'm interacting with state. I'm looking at state. If you're using React, this is a very fundamental thing in React. If you're using any view layer, this is fundamental to that. Of here's my DOM. I do something, here's my DOM. Or I have a query. I have an empty array. I query, I get a new array. I don't want to tell my computer how to do that. Instead, I want to describe what it should end up as. I want to describe to my code in a declarative way, hey man, figure it out. So let's revisit our original problem. We have all these ideas now. We have all these cool words in our head. And now we're going to ask ourselves, given this board and given these rules, how do I do this without affecting implicit state? Without hurting another worker's chance of doing their job correctly? How do I do this? And it breaks down to, what do we want to tackle first? Do we want to deal with state, or do we want to deal with math? This is basically our question always. And the truth is, they're both really hard, right? Like, no one's going to pay me to paint in the lines. I wish they did, because I would not be coding. But what we get paid for is to solve these really hard, complex issues. But what I've found is that if I do it in object-oriented, if I do it imperatively, if I do it functionally, I have to solve the same issues. I have to explain to my computer to do the same thing, to follow the same steps. So let's suppose that we decided to do functionally, right? Well, one of the first problems we're going to have to solve is, given a list, find out certain locations of certain things, right? So here we want to find out the empty indexes. So how do we do that? How could we talk to our computer and say, hey man, I want you to filter something. I want you to get only if. Well, we can just write a filter function. And this filter function takes an array and it takes a predicate. Predicate's a fancy word for a function that returns truthy or falsy. And we say, hey, just like map, just like for each, iterate over this list, and if this item passes our test, if this item returns truthy after going through our function, return it to me. So now, if we use this, we get all of the empty ones. So we say, hey, filter the values with this function that takes a char and returns true or false if the char is equal to an empty, or to a period. But that's not what we wanted. It's halfway there. What we wanted was the indexes. We wanted to know where in this array there is an empty element. And lucky for us, years ago, projects ago, in a totally different environment, maybe in a totally different language, we solved how to do that. We solved how to transform an array into what we wanted with map. So here we can reuse this function. We can reuse map to solve a totally different problem. So here we take our values array, and we pass it a function. And this function expects two arguments, a value and an index. And it returns to us an object of location and val. And you can see at the end of this, we just get an array of location 0, val dot, location 1, val dot, and so on and so forth. And since we're in JavaScript, and since we're so lucky to have one of the easiest languages to learn, arrays come with these. And they're tuned in C++ and in super hard stuff that I don't understand. They're tuned to be super performant. And because map is a value, because filter is a value, we can chain them. We can say, take vals, take this array, call the map method. Just like our other map method, it expects a function, and it returns a new list. Vals.map is equal to an array. This vals.map is equal to this array. And because it's equal to an array, we can use the filter method of that array. So now we're seeing that when we start producing things instead of affecting things, we're creating longer and longer tubes. We're creating longer and longer transformations of this data into what we need. So how does that affect us at all, right? We have this board, we have this array of arrays, we're doing functional, we figured out some toy problem that we don't really quite understand yet. But here's our data structure. We have an array of rows, and each of those rows is an array of columns. So if we wanted to get 0, 0, it'd be 0, 0, and that's super duper easy, right? But let's say we wanted to get x1 and y2. We would do this. Y comes first because it's the rows, x comes second because it's the columns. So now that we know how to filter, we know how to map, we have almost every single piece that we need to solve this problem. And here's how I solved it. A whole bunch of math. Half of this is confusing, and I don't quite understand it, but the interview went well, so I guess it was good. This is the only two things we should worry about, right? Everything else is using the data to figure out an answer, but these two things manipulate it. So this is inside of my make board function, and my make board function takes a board and a new center. So we're going to look at get mine coordinates. Get mine coordinates is going to take our board that was given to it. So whatever board's given to it, I don't care. I don't care if it's the right board. I don't care if it's the wrong board. I don't care if it's a practice board. I'm given a board. And this board, I'm going to map over the rows. And for every one of these rows, I'm going to map over the column, just like we did before, and create an object. So I'm taking this board and I'm making it into the data that I want. I'm making it look like what I need it to look like. And then once we have it into an object, I want to make sure that I'm only getting the ones that aren't empty. So I'm saying, hey, give me this cell, the cell being this object that we made, and now grab the character that we set here, and return true if this character is not equal to an empty square. And then I only want the location. I only want this double, so I return it there. And sometimes we'll find that filter returns an empty array. Sometimes nothing passes that, so it returns an empty array. And that made it really hard to think about, so I just threw this in there. And because we have these ideas, because we have this fundamental understanding of filter and map and transformation, we can just start tagging things on. We can say, oh, this is kind of what I want, but I need it to only be something else. And okay, cool, this is kind of what I want, but I need to transform it into something else. And this whole map is kind of what I want, but I need to change it a tiny bit more. And we can focus on these small, tiny, testable functions instead of focusing on this huge board. Now, get max diff is even more confusing, but basically we're given our new center from our original function. Our new center is a double. This double is just an XY of where you're at in the board, and our targets. Our targets is what we produced here. And then we map over the targets, and we're going to get the biggest numbers. I want to get the biggest deltas, is basically what I'm doing here. So that's what this line does. So now we've created a new array of our deltas, and we're going to get the biggest one of those with our reduce. And I will show that after the presentation. So let's look at get biggest numbers. Get biggest numbers takes a lot of arguments, as many as you want. And it spreads them out, I guess is the correct term, into an array. And this array we're going to reduce into the biggest one. All I'm worried about here is I'm trying to find out from my position how far left, how far right, how far up, how far down do I have to go. And this gives me the dimensions of my board. So we finally solved it, right? We can now print the board. We've finished step one, and it was super hard. We spent a lot of time. We had to push our project manager back a day or 5, but we solved it, right? But now that we solved this issue, now that we've done what we were supposed to do, what else can we do? Well, we can print the board. We solved the actual one thing we were told to do. But we can also get the max delta, right? So maybe at some point in the future, I want to say, hey, how far is a point? Give me the farthest point between here and there. We figured out a way to do that. And maybe I want to get the biggest number from sets of doubles. Maybe I want to get the biggest x and the biggest y values. We had to solve that. That was an issue that regardless if we did it in OOP, regardless if we did it in imperative, these problems had to get solved. But because we solved this in a functional way, because we solved this in a way that is not dependent on implicit state, we can reuse them across the board, across languages, across code bases. So I wanted to just give you a brief overview and kind of just take questions and then start nerding out about what you guys want to learn about. So here's just a too long didn't read about the talk. What we do is hard, guys. There's no easy thing. There's no easy way to code. But what we find is that most of these problems repeat themselves, right? In our student list, in our students thing, we had to do map. We had to solve that issue. But we saw that we can reuse map. We can reuse filter. We can reuse for each across different problems because we abstracted the problem away from our state. But like I said before, this isn't functional versus. This isn't OOP is bad. This isn't you can only do it one way. Functional is just another approach. Functional is a way to look at problems that I find easier, but I use object-oriented all the time. I'm a front-end developer, and I have to use the DOM. I have to use objects. When I'm in PHP, I have to use objects. If I ever touch Java, I have to use objects. But sometimes, just maybe, we can start thinking about these problems in a functional way, in a way that's not dependent on a this keyword, that's not dependent on the arguments outside of the function. Maybe we can start thinking of problems in, okay, if I'm given this input, how do I make it into the output that I want? So that's all I have. Cool. Well, thanks, guys. Hopefully I didn't just confuse you all and just talk about nothing. So